So for example number 3 in your textbook, we're going to keep working on linear approximations. And one thing that's a useful, I guess, useful product of this is that if I were to take this binomial expansion, a generalized binomial expansion, I can approximate the value using linearization. So using the linearization methods, we find that depending on the values of k and x, I can approximate the numerical values. Now, truth be told, to expand a binomial, it's a little more complicated. If k is like a large number, like say 5 or 6, what happens is I have to multiply the stuff inside of the parentheses by itself 5 times, right, to get an answer. And so this is a short, quick way to kind of approximate it. So what they did in example number 3 is they gave us 4 different scenarios. So I'm just going to crank through them one at a time. So they said, all right, whether you guys realize this or not, this is actually a binomial expansion. Because we could think of it as 1 minus x raised to the 1/3. Well, if that's the case, then we would say that k is equal to 1/3, and that x is equal to x in this case. So nothing real fancy. Actually, negative x or something along those lines if you want to think about it. So the x term is equal to negative x. And that's a little confusing, but that's what it is. What I'm saying is that this is the formula, and then these two things go in each other's place. So if I wanted to approximate the value of this, then I'm simply going to write in 1 plus k, which is 1/3, times x, which is negative x. So then I could say that this is 1 plus 1/3, actually negative 1/3 x. Okay? And that's it. And your textbook actually writes it this way. I keep writing the plus sign. Negative x over 3. And so whatever value for x I plug into the original function, if I plugged it into this linear approximation, it would be very close, just like the other problems we did before. Does that make sense? All right. So let's do another one. Can I switch screens, move on to the next one? All right. So now another scenario would be something like this. B, I have 1 over 1 minus x. Well, that too is a binomial expansion to some degree because it's really 1 minus x all over negative 1. So remember that, and I'll do this a little different. If I say 1 plus smiley face, we'll do winky face, raised to the k, the linear approximation, whiteboard's not being very nice today, is 1 plus k times winky face. Okay? So the approximation of this is 1. Now k is negative 1, so I'm going to say minus 1 times whatever my smiley face is, which is negative x. So let me write this out. So it's like plus minus 1 times negative x. All right, so the negatives cancel, and I would say that that's approximately 1 plus x, right?
Yes.
So whatever value I get for that, and I plug it in, I can get an approximate value. Does that make sense? All right, may I move on to the next one?
Yes.
Okay. So another scenario that the book chose for us to play around with was C, which is the square root of 1 plus 5x to the 4th. All right, so now this is the same as 1 plus 5x to the 4th raised to the 1/2. And so let's remember that whatever 1 plus winky face raised to the k can be approximated through a linearization method, and that approximation is 1 plus k times winky face. Now the reason I'm using winky face is I don't want you guys to get confused with the x and the x and all that stuff. Although I don't think you would, but just to be on the safe side. So then now let's label this. In this particular case, my winky face is equal to 5x to the 4th, and my k value is equal to 1/2. Okay? So if I took this and expanded it, which I can't really, because when you raise something to the 1/2, like how do you, that's not that easy to do. Right? So what I would need to do is I would approximate this as 1 plus k, right? What's k? 1/2 times winky face, which is 5x to the 4th. And that reduces down to 1 plus 5 over 2x to the 4th. Okay? That's pretty easy. Now you can see the value in this if you had something raised to like the 27th power or something like that. And then what you would do is you would have arbitrary values for, say, x. So if I said x equals 2, like so if I were to plug this into a calculator, if I were to let x equal 2, it would be 2 to the 4th power times 5 and all that stuff. So let's just double check and see how close we are with the approximation. And it says for small values of x. All right. So what would be like a really small value? 0.1. 0.1 is something that we can plug into this thing or something like that. So in other words, let's clear this. If I were to take the square root of, what was the original function? 1 plus 5x to the 4. All right, so if I say plus 5 times, and then we're going to put 0.1 raised to the 4th, right? So I'm just arbitrarily choosing 0.1, and I enter that in, that's what I get, is I get pretty darn close to 1. Okay? That makes sense? All right, now from there, if I were to say 1 plus 5 times 0.1, okay, raised to the 4th, divided by 2, right? Isn't that the same thing? I get pretty close to the same thing. Does that make sense?
Yeah.
So that's what that is. So you can take a very complicated binomial and find a linear approximation rather easily.